So we're about to embark on a new topic, which is the topic of eigenvalues and eigenvectors, which will be sort of a combination of theory and then the theory leading to algorithms. And the algorithms will be distinctly different. The algorithms will be inherently So the algorithms for solving eigenvalue problems are inherently iterative in nature, which means that we don't go through a set of computations and then have the answer. Instead, we're going to be converging to the result. Okay? And this is actually inherent in the problem. Almost there. Okay. I'm going to clap so that I can sing, okay? We have a synchronization point. Hopefully that works. All right. So the algorithms are going to be iterative in nature. And the reason for that is that inherently you cannot compute the eigenvalues exactly in a finite number of steps. And this all goes back to trying to find a formula for the roots of a polynomial of degree greater than 5 or greater. There's something called the Galois theory that can be used to prove that you cannot do that. And because eigenvalues are closely associated with the roots of the characteristic polynomial of the matrix, that result carries through in not being able to find a formula for the eigenvalues of a matrix of size 5 or greater. Okay. Now, let's remember a little bit how we go about finding eigenvalues and eigenvectors. And I probably should have started with a concrete example, but let's just put something out, okay? First of all, what is the algebraic eigenvalue problem? The algebraic eigenvalue problem always deals with square matrices. So we're going to be concerned with matrices that are n by m. And what we're after are, given matrix A, we want to find vectors x and scalars lambda, such that A times x is equal to lambda times x. Now, what does this mean? Okay. Notice that given a vector x, applying A to it means that you're applying a linear transformation to that vector x. Right? You're taking it next door. I wonder if I sound too dumb like that. Very loud, right? That sounds more like a movie or something. Okay. Anyway, so applying A to x is applying a linear transformation, right? L of x is equal to A times x. The question you're asking here is, what direction x, vectors remember are directions, is such that if you apply the linear transformation for it, the net effect of that is that you simply scale the vector. Now, why is that important? Well, it turns out, for example, to be extremely important in structural analysis in engineering mechanics. You know, if you have a car and you're going over bumps and you hit the bumps at just the right frequency, everything starts to rattle. Well, that used to be true for cars back in the 60s and 70s. By now, car makers have very complicated, accurate enough models of what happens when a car rattles to know how to dampen it. Okay? Dampening means that you're trying to make these eigenvalues small so that every time you hit a bump, A, you decrease the vector. Okay? So you hit a big bump and the shocks absorb that and they dampen in the direction in which the shock sent your car. Okay? If, on the other hand, that is greater than 1, then you hitting that bump actually increased the direction in which you got hit. And then when you hit the next bump at just the right frequency, you do that again. And what happens is that eventually your car gets out of control, you lose control, you go over the side of the road, horrible things happen. Okay? Or worse, the rattle is bad enough that people aren't willing to pay money to buy the car. And that's why car companies are very interested in this. So A somehow captures the operator that describes the car. The eigenvalue problem is what tells you whether or not the car rattles. That's one way of thinking about it. Another way of thinking about this is, imagine standing behind a swing. There's a direction when you push your friend on the swing, where if you push hard enough, you keep going higher and higher, right? Now, there are actually two such directions, right? If you have your swing, going in this direction, then if you push the right way, everything is nice. If you start pushing in this direction, everything is nice. If you push sort of sideways, it starts going in an oval. The two eigenvectors are those directions. So roughly, this is how I as a layman think about this. I see swings. And then I immediately translate it into math and I'm much happier. Okay, so we're going to do some math. But the important thing is, the eigenvectors are the directions in which the operator simply acts as if it's a scalar. Okay? So this is known as the algebraic eigenvalue problem. A is given, the vectors and the scalar are to be computed. Lambda is known as an eigenvalue. X is then known as an associated eigenvector. Lambda comma x is known as an eigenpair. And the first thing you notice is that, first of all, x equals 0 is probably not particularly interesting, right? So we don't consider the 0 vector to be an eigenvector because we really want a direction, and 0 doesn't really have a direction. And the second thing you notice is that eigenvectors associated with a given eigenvalue are not unique. Why? Because if you scale x, let's see. A times alpha x is equal to alpha times A times x, which is equal to alpha times lambda times x, which is equal to lambda times alpha x, and bingo, I've created a new eigenvector. Right. And this is because we're interested in the direction in which the operator acts as if it is a scalar. It's a direction, it's not a length associated with it. All right? Good, we've got that. And then the other thing you notice is that if it's the case that A is x is equal to lambda x and A y is equal to lambda x, then what do you know? You know that A times x plus y is equal to A times x plus A times y, which is equal to lambda x plus lambda y, which is equal to lambda times x plus y. And what you notice is that if you have two eigenvectors associated with the same eigenvalue, and of course these could point in different directions. Yes?
Ay is lambda x, right?
Left hand side.
On the left hand side it must be Lambda weight.
Oh, yes, of course. All right, there. Thank you. This is why I should be looking at my notes. Anyway, what you notice is that if you have two directions in which the operator acts as if it's a constant, then adding those two directions gives you another eigenvector. And as a matter of fact, it's not hard to see that A times alpha x plus beta y, in other words, any linear combination of eigenvectors will give you yet another eigenvector. And what that means is that the eigenvectors associated with an eigenvalue form a substance, if you remember what a substance is.
In this one example, isn't the diagonal direction a linear combination of the two vectors you talked about?
Isn't the diagonal?
So,
Oh, this here?
yeah.
Yes, but notice that these two directions would be associated with two different eigenvalues.
Okay.
Okay? And that's the difference.
Okay.
Right? And you can show that if you have that ax is equal to lambda x and ay is equal to mu times x mu times y, then you can show that x and y must be linearly independent. Let's see if we get to that point somewhere. Otherwise, I'll throw it in this exercise. You can do that. Okay. So, now, there are different ways in which it becomes worthwhile to look at the problem. Okay. And the most important way to look at it is to say, we know that ax is equal to lambda x. We can therefore write this as 0 is equal to lambda x minus a times x. We could then factor out an x. Except we don't know how to subtract a matrix from a scale. Right, so that's what we would like to do, but what do we have to do in order to make that happen? We need to put the identity in there, right? We should recognize that lambda ix minus ax is the same as this. And then all of a sudden we can pull this out. Okay? And notice that we know, therefore, that lambda ax equals lambda x if and only if lambda I minus a times x is equal to 0. And of course, sometimes people write this as a minus lambda I. We're going to write lambda I minus a. Same difference, okay? Okay? And now, all of a sudden, what do you notice? What you notice is that this, now we're interested in a non-zero vector x. And what you notice is that we have all kinds of ways of now describing lambda. Okay? Lambda is an eigenvalue of A if and only if all kinds of special things are true about this square matrix, namely what? Whole bunch of equivalent ways, and what you want to do over the course of the next couple of weeks is pick and choose the one that is most convenient for whatever it is that you're trying to accomplish. If this is true, and there must be an x that is a non-zero vector, what do we know about this matrix?
Singular.
It must be singular. What's another way of saying that it's singular?
Determinant is 0.
What else?
Less than n.
Rank
rank, so let's say that rank of lambda I minus A is less than M. Good. Another one?
We have, it has to have a this matrix has to have a singular value of 0. We'll get to that point later. This is sometimes called a shifted matrix, and what we're saying is the shifted matrix must have a 0 eigenvalue. So, correct. Yes?
Linearly between rows and columns.
Columns of lambda I minus A must be linearly dependent. What else?
All of the rows must be perpendicular to X.
All the rows must be particular. So what you're really saying, X is in the row space of A.
When you multiply them out.
Yeah. Not that. Lambda I minus A. Right? Yeah, that's another one. Okay. The point is, there's a whole bunch of statements that most likely in an undergraduate class you were given as being equivalent to matrix A being singular, or either that or you were given a long list of things that were equivalent to A being non-singular. And any of those conditions you can use to describe lambda I minus A, and it becomes convenient sometimes to pick one or the other. Okay? But the important insight here is, in order to find all of the lambda that satisfy this, what you're really doing is you're looking for all of the lambdas that make this singular. And the fact that the determinant is equal to 0 is a convenient way of describing that. Okay. Now, some undergraduate courses go into great detail as to how to compute the determinant of a matrix. Okay, and there is actually a physical interpretation of the determinant. The absolute value of the determinant is actually the volume of the multi-dimensional, what do you call it?
Unit.
Whatever that thing is called, okay? In 3D, you take the columns of A, and then you look at the parallel, no, not whatever it's called, okay? I can't even pronounce it, right? And actually, the volume of that is the absolute value of the determinant, and you can then recognize that if that all collapses into a subspace where one of the dimensions is missing, then you have columns that are linearly dependent and bad things happen. Okay? So that's how all of those are related. But the fact is that beyond 3 dimensions, the determinant is not a particularly useful thing to compute. Okay? I know that you were taught to use it in Cramer's rule to solve linear systems. That turns out to be merely something that high school teachers use to punish you rather than have any kind of useful. It's not a useful algorithm. It turns out to be exponential positive. Unless you do an LU factorization to compute it, in which case, you have something that you can solve with already anyway, etc., etc. So determinants are useful for 2x2 and 3x3 problems. You probably remember what that's all about. For example, let's go back to the problem I was trying to set up, making this up as I go along. If we were to look at this, and we then look at the determinant of this, then we would be looking at the determinant of lambda minus 1, lambda minus 4, minus 2, 3. And if you look at that, you may remember that that's this times that minus this times that.
Your non-diagonal must be negative.
Oh, yeah. Thank you. And what you get is lambda minus 1 times lambda minus 4 minus this times that is minus
6, and then you would manipulate that into a quadratic, and you would solve for the roots, etc. Okay? And then similarly, if you ended up with a 3 by 3 matrix, what you would do is you would compute the determinant of the 3 by 3 matrix after subtracting off of the diagonal. Often, in your undergraduate class, you probably were looking at this minus lambda I, which is why. But anyway, you get the point, okay? And then, if you were taking an honors class, you would be asked to do so for a 4 by 4 matrix. But what you would very quickly run into is that you don't know the formula for finding the roots of a 4 by 4. It actually does exist. It's just nobody has it at their fingertips. As a matter of fact, nobody has it for a polynomial degree 3. Nobody has what the roots of that polynomial are at their fingertips, right? I certainly don't. And it turns out that you can theoretically show that for a polynomial with degree 5, it doesn't even exist. What's important is that when you start with a 2 by 2 matrix, you end up with a polynomial of degree at most 2. When you start with a 3 by 3 matrix, you end up with a polynomial of degree at most 3. When you have a 4 by 4 matrix, you end up with a polynomial of degree at most 4, etc. Which you can show if we actually came up with a formula for the determinant. And the important thing, therefore, is that we can say something about the eigenvalues of a matrix. For example, we know that there are at most m of them, possibly with repeated roots of the polynomial, therefore possibly repeated eigenvalues. We also know things like if you start with a real valued matrix, you'll end up with real valued coefficients in your polynomial. But you know that if you have real valued in your polynomial, you may still have complex valued roots to that polynomial. And what that means is that the roots of a real matrix may actually, the eigenvalues of a real matrix may actually be complex valued. But we also know that those roots then come in conjugate pairs. So we know that if you start with a real valued matrix, then you end up with possibly with complex roots, but they will always come in conjugate pairs, and all of those kind of duties to sort of follow from what we know about polynomials. Right? So that's how the characteristic polynomial comes in handy, because it allows us to immediately recite all kinds of results about the roots of polynomials and use those for the eigenvalues. But other than that, it's not at all a practical way of finding eigenvalues of a matrix. All right? Good. So, this here, for us, is a theoretical tool. Except that sometimes we may want the roots of a 2 by 2 matrix. As part of a practical algorithm for finding the root. We may want the eigenvalues of the 2 by 2 matrix as part of an algorithm for finding the eigenvalues of the general matrix. Okay? All right, so we're moving along with the theory. Where am I? Done that, I've done that. That. Okay, so in the notes, I show how if you start with a polynomial with certain coefficients, then you can come up with a matrix that has that polynomial as its characteristic polynomial. And that's obviously important because that indeed means that if you have a formula for finding the eigenvalues of a general matrix, then you could use that formula to find the roots of a polynomial, and we know that you can't have that for polynomials of degree greater than 5. Okay. Okay. So, now, there's a couple of definitions we need to go Okay, we have this, we have that we often want to look at this problem as follows. And we have that the determinant of lambda I minus A comes into play. And what we're going to do is we're going to call that the polynomial of degree at most m of lambda. Okay? And that is the characteristic. Okay. We also can define E sub lambda of A, and let's define that to be the space of all vectors x such that Ax is equal to lambda x. So given an eigenvalue lambda, think of this as the set of all possible vectors x that are eigenvectors associated with lambda, except that we also throw the zero vector in there. Okay? Because the zero vector we usually don't consider an eigenvector. And the fact is that we sort of informally argued that this is actually a subspace. Any linear combination of vectors in this space is also in the space, and that makes it a subspace. That's actually an exercise you're going to do for homework. And what that means is that we can think about the dimension of this space. And what does that tell us? That tells us how many linearly independent, how many vectors that point in different directions we have associated with lambda. Okay? Now, let me try to say, let me see where I am. Just try to stay on schedule here. Okay. One thing that we know is that the roots of this polynomial may have multiplicity greater than 1. What does that mean? It means that when we factor, notice that we can factor p of lambda as lambda minus lambda 0 times lambda minus lambda 1, etc. Right? But what we know is that some of these might actually be equal to each other. Okay? So, if lambda is a root of multiplicity what should we call that? What do we call it here? Okay. Is a root. Then lambda is said to be the eigenvalue of algebraic multiplicity how many times eigenvalue shows up as a root of a characteristic polynomial is the algebraic multiplicity. Obviously, if we have an algebraic multiplicity, we must have some other kind of multiplicity as well. And it's the dimension of the associated subspace of eigenvectors that is the geometric multiplicity.
You're saying it's the magnitude of that set?
It's the number of elements in that set. It's the number of roots. Okay? That's the multiplicity. If lambda has, let's call it k tilde linearly independent eigenvalues associated.
Eigenvectors?
Eigenvectors. Then k tilde is the geometric. And it's easy to show that if a vector is an eigenvector associated with one eigenvalue, then it can't be an eigenvector associated with another eigenvalue that's not equal to it. Okay? So what does this all mean? Well, let's put some subscripts on this. And let's let, by the way, capital lambda of A is the set of all vector lambda such that A times x is equal to lambda x some x not 0. So that's a set of all eigenvalues. This is known as the spectrum of A. And what else do we have? We know that obviously the number of elements in the spectrum of A is the number of distinct eigenvalues. So we can write this as lambda 0, lambda 1 through lambda k minus 1, where this is the multiplicity, right? Distinct eigenvalues, right? I need to come up with a different number there, and that number letter. P. I don't. Well, actually, R would be better because the number of distinct eigenvalues. No. All right, here we go. Fair enough. What do we know? If we know that the sum over all such indices of the multiplicity of that eigenvalue has to be m. Why? Because m is the total number of roots counting multiplicity, and this counts all of the multiplicity of the roots. Okay, so we know that. It is not the case that if you add all of the geometric multiplicities together, you end up with m. Okay? So it's possible that you have fewer linearly independent eigenvectors then you need to span the space or Cm. Now, where in the world does that come from? Well, if you look at the matrix that has the form mu on the diagonal and 1's on the superdiagonal. Okay. This is an upper triangular matrix. You happen to remember how to find the eigenvalues of an upper triangular matrix? They're all on the diagonal. Okay. Why is that? Because if you subtract from this matrix an element on the diagonal, you end up with 0 on the diagonal. If you have 0 on the diagonal of a triangular matrix, you end up with a singular matrix. Okay. So it's easy to find all of the eigenvalues of the diagonal of a triangular matrix. And of course, a diagonal matrix is a special case of a diagonal matrix. So the same observation holds for a diagonal matrix. Okay. If you subtract, now clearly mu is the only eigenvalue of this, and it has algebraic multiplicity equal to the size of this matrix, right? But if you look at mu I minus j of mu, you get the matrix that has zeros on the diagonal and minus 1 on the superdiagonal. And it's not hard to see that all of these columns are linearly independent. You can't take linear combinations of those columns and construct a zero vector from it without taking coefficients of all zeros. And therefore, it only has one linearly independent vector in its null space, and because it only has one linearly independent vector in its null space, the null space has dimension 1, and therefore it has geometric multiplicity 1. What is this kind of matrix called? It's a Jordan block, right? Which is something mathematicians love, but has absolutely no practical purpose whatsoever. Okay? There's this theory that says that you can always use, you can, there you go, we'll get to that. No, we're not going to get to that. It's useless. It's only useful in showing that indeed matrices can have eigenvalues with geometric multiplicity less than the algebraic multiplicity. Okay? That's the only way in which Jordan blocks, I think, have practical value. Maybe in some mathematical way to have theoretical value. We're not going to bother ourselves with that. Okay? Now, why is it that we don't like Jordan? So I'll sort of point to you what the theory is, and then I'll point to you out why we don't like it. Okay? So here's the theory. Notice that it's really easy to find the eigenvalues of the diagonal matrix. You just read them off the diagonal. And it's really easy to find the eigenvalues of an upper triangular matrix or lower triangular matrix. Okay? So, wouldn't it be, what did we do in all of our methods so far? We took a matrix, we did some sort of factorization, and then that factorization made it easier to solve with the matrix. Okay? Wouldn't it be nice if there was a magical way of taking a matrix, transforming it into an upper triangular matrix or a diagonal matrix so that we can read off the eigenvalues so that we're done? Okay? Now, to do that, we need to somehow transform the matrix while preserving the eigenvalues. And to do that, we need the following observation. If you have a matrix A, make sure I'm consistent with my notes, and from that you create a matrix B by multiplying from the left and the right with a matrix Y, well, Y inverse AY. This is known as a similarity transformation. Then it's not hard to see that the eigenvalues of A are equal to the eigenvalues of B. How do you do that? Well, you know that if we know that AX is equal to lambda x, then you can always multiply both sides by y inverse. And you can always multiply in the middle here by the identity. And then you can always put some parentheses in various places. And what you get is matrix B here, such that if you multiply this, you get lambda times y inverse x. And then you can call this y. And what you've done is found a vector that is an eigenvector associated with lambda. And you know that that's the zero vector if x is not a zero. Sorry, you know that that's not a zero vector if x is not a zero vector, because we're clearly assuming that y is invertible, and therefore this cannot be zero. Okay. So what does this mean? It would be great if we could find a matrix Y such that this here becomes a diagonal matrix or an upper triangular matrix, because then we could just read off the eigenvalues on the diagonal and we would be done. And that's why often when you talk to mathematicians, this topic of finding eigenvalues and eigenvectors is often called diagonalization. Diagonalization of matrices, okay? Because what they want to do is they want to somehow make this matrix into a diagonal matrix. Okay? Notice there's some similarity there with the singular value decomposition, right? And again, just like with the singular value decomposition, we said if you can only find the right basis for the input and the output when you do A times X, then the matrix starts acting like a diagonal matrix. The exact same thing happens here, and hopefully I'll remember to touch on that as we go. I mean, in some sense, you can see that here. If this were a diagonal matrix, here we're expressing X as the coefficients in the basis where you take the columns of Y to be the basis, and the same thing for the output. Okay, diagonalization. So, the good news is similarity transformations preserve eigenvalues. If you can therefore make the matrix diagonal, you can read off the diagonal entries. And by the way, the eigenvectors associated with the diagonal matrix are just unit basis vectors. So those are really easy to find as well. That's the good news. And obviously, you can figure out how to compute the eigenvalues of A from the eigenvalues of B, because you have this way of transforming the vectors back and forth. So that's the good news. The bad news is not all matrices can be diagonalized. So let's start with matrices that can be diagonalized. There are a few little things that... So, let A have m by m, have m linearly independent eigenvalues. Eigenvectors. What does that mean? That means that every eigenvalue has algebraic multiplicity equal to its geometric multiplicity. Every eigenvalue you can find a full set of eigenvectors. By the way, that means that A is said to be non-defective. So if somehow you can't have a full set of eigenvectors that are linearly independent, then the matrix is somehow defective. Okay? A Jordan one is defective. Okay. Then there exists a y such that y inverse AY is diagonal. Which then means that we can find the eigenvectors as diagonal. Turns out this is not that hard to prove. What do we know? We know that A times y sub I is equal to lambda sub I y sub I for y sub 0 and y sub n minus 1, which are linearly independent. Why? Because we said there are n linearly independent. Anytime we have sets of vectors, what do we like to do? We like to take them and put them together into the columns of the matrix. And often we start with the matrix and we like to think of it as columns. Now we're taking vectors and we're making them into the columns of the matrix. Let y be equal to the matrix that has these vectors as its columns. What do we know about y? We know it's square. And we know that it can be inverted because it has linearly independent columns. That's something you learned in undergraduate linear algebra. We also know that A times y is equal to the matrix lambda 0, y0, lambda 1, y1, through lambda n minus 1, yn minus 1. Why is that? Because A times this, that's the same as A times the individual columns. But that from this assumption means that we can replace each of the individual columns by that. How can we somehow make this into a matrix that has y0, y1 as its columns? In other words, how can we somehow pull all of the eigenvalues out? Hopefully something diagonal comes out, right? Well, if you put this as a diagonal matrix on its right, notice that multiplying from the right by a diagonal matrix means that you multiply the individual columns by the corresponding elements on the diagonal matrix. So what do we have now? We have that A times y is equal to y times some matrix, let's call it lambda. Here's always lambda. Okay? And then because y is invertible, we know that y inverse a y is equal to lambda. Fair enough. So, given a full set of linearly independent eigenvectors, we have the columns of the matrix A that will diagonalize the matrix with a singularity, that become the matrix that you use in the singularity transformation that then transforms the matrix into a diagonal matrix, and then you can find the eigenvector. And as a matter of fact, we can take this argument backwards and show that this is an if and not an if. So, if the matrix can be diagonalized, then you can read the eigenvectors off of the columns of y. If you know there's a full set of eigenvectors, then you can use those to create the matrix with diagonals. The unfortunate part is that not all matrices have a full set of eigenvectors. And this is where the Jordan block comes in, because what you can show is that for every matrix, you construct a y such that you don't end up with a diagonal matrix, but you get a matrix that's almost diagonal, except that on the diagonal you have Jordan blocks associated with the different eigenvalues. And you would think that that's pretty powerful. But it's not powerful at all because we don't like matrices, arbitrary matrices, that may have linearly independent columns, but for which we don't know how quote-unquote linearly independent they are. Right? We have learned that when you work with matrices that have a poor condition number, all kinds of weird stuff can happen, and therefore you can't trust the computed value. And if you can't trust the computed value, then you may end up having to hire a lawyer to defend yourself against your clients who are upset because you didn't get very good values. Okay? So, the question then becomes, what do we do instead? Okay? In the past, when we decided that we didn't want to use matrices with poor condition numbers, what did we do instead? We turned towards matrices that had really good condition numbers. And what kind of matrices have really good condition numbers? Unitary matrices. Okay. So, what we're going to do eventually is we're going to come up with algorithms that only use unitary matrices, which is a good thing because they don't amplify error. But as a result, we're not going to diagonalize the matrix, at least not when the matrix is not symmetric. What we're going to do is we're going to instead make the matrix upper triangular, but that's okay because then we can still leave the eigenvalues of the diagonal. And to do that, we're going to prove the theorem that's known as the Schur decomposition theorem. And what you're going to recognize is that the proof of the existence of the Schur decomposition theorem is very similar to the proof of the existence of the singular value decomposition. Okay, let's look at that. Though my shoe is untied, I'm going to try not to trip here. Let's see if I don't trip up. So the Schur decomposition theorem is, should probably be called the fundamental theorem of the algebraic eigenvalue problem. And this is how it goes. Okay. Let A be the square matrix. Then there exists unitary Q and upper triangular U such that A is equal to Q, U, which of course is the same as saying Q Hermitian A, Q is equal to U, which relates more to what we have over there, which of course is the same as Q inverse A, Q is equal to U, because we know that the inverse of a unitary matrix is its Hermitian transpose. So in other words, what this says is there's a unitary similarity transformation that transforms A into an upper triangular matrix, and once we have an upper triangular matrix, we can easily find its eigenvalues and actually its eigenvectors. You with me? Now, the proof of this is a little bit tricky, but it's quite similar to the proof of the existence of the singular value decomposition. Now what I did for the proof of the singular value decomposition was I kind of gave an outline of how one should go about it, and then I actually gave the formal proof by induction in the notes. This time I got lazy. I will give you a feeling of what's going on, and then hope that you can relate it to how the proof of the existence of the singular value decomposition went, to recognize that you can make it into an inductive argument that proves the actual existence. Fair enough? And as a result, it'll all go a little bit faster. Okay. So, so here it goes. We know that there is a characteristic polynomial A. And we know that this characteristic polynomial has roots. We don't know how to find those roots, but we know they exist. And in particular, we know there's at least one root. Okay. So let's let lambda 0 be a root of the characteristic polynomial A. What does that mean? We know that there's at least one eigenvalue. Okay. Now Q sub. Have you ever noticed that I selectively index starting with 0 or 1? You may have noticed that this always fits into the algorithm as I like to then express it, okay? Anyway, curious. Let Q1 be such that A times Q1 is equal to lambda 1 Q1 with length. We know the eigenvalue exists, therefore we know that there is at least one non-zero vector associated with it. We can always take the eigenvector and normalize it to have length 1. We get a new eigenvector. That's the one we're going to use. Okay? The second thing we're going to do is we're going to let Q be the matrix that has Q1 as its first element, its first column. Q must have n columns because we're going to make it into a unitary matrix. And we know that we can find n minus 1 more vectors that are mutually orthonormal and that are orthonormal with respect to Q1. Okay. We're just filling out the basis for Cn. Okay. So we can make it unitary. Okay. Now, let's see what happens if we look at Q Hermitian AQ. It sure would be nice if this were actually diagonal or upper triangular, because then we would be done. But of course, because we don't really pay much attention to how we pick Q2, we can't be quite that lucky, right? But let's see what happens. Well, we have a partition matrix, so we can do Q1, Q2, Hermitian A, Q1, Q2, which then is equal to Q1 put on its side, Q2 put on its side times A, and we might as well go ahead and multiply this out. We get A times Q1, A times Q2. That's just multiplying A times the columns is the same as multiplying each of the individual columns. And then that can be written as an outer product of two symbols times something with two symbols. So we get a 2 by 2 matrix of symbols, and we get Q1 Hermitian A, Q1, Q1 Hermitian A, Q2, Q2 Hermitian A, Q1, and Q2 Hermitian A2. But we know that this is just lambda times Q1. And we know that this is just lambda times Q1. And that, of course, means that this is just, oops, that should be lambda 1. And that just means that lambda 1, that this is just equal to this right here. And this is equal to Q2 Hermitian Q1 times lambda 1. And this, of course, is just 1. So this entry here becomes lambda 1. And these are all orthogonal to Q1. So we know that this becomes a column of zeros. This here we can't say a whole lot about. So what we can do is we can call that W Hermitian transpose, just something. And finally, this we don't know much about, but we can call that B. And you can imagine that you can then continue with B to pull off another entry. What you'll have to do, what you end up with, is having to bring out the unitary matrices and multiply them together to get a new unitary matrix, which is then actually the unitary matrix that we want. And we're done. Eventually, this becomes all right? So, that's really powerful. So that's known as the Schur decomposition. And this is known as the Schur decomposition theorem. Okay? Now, if A is Hermitian, then A is equal to Q U Q Hermitian transpose, and A Hermitian transpose is equal to Q U Q Hermitian times Hermitian, which is equal to Q U Hermitian Q Hermitian. So what we get is that this is equal to that, and if that's equal to that, then we know that U must be equal to Q Hermitian, but U is upper triangular and this is lower triangular. So what do we know?
It's diagonal.
It must be diagonal. And what else do we know? The diagonal elements must be real. Right? Because on the diagonal we end up with the conjugates of the diagonal elements, and if those are equal, then those elements must be real. So, all kinds of things we notice. Eigenvalues of a Hermitian matrix are real. A Hermitian matrix is diagonalizable. It can be diagonalized with a unitary matrix. If you have two eigenvectors associated with two different eigenvalues, they're orthogonal to each other. You can pick the eigenvectors of a Hermitian matrix to be mutually orthonormal. Okay? So obviously, Hermitian matrices are wonderful. Right? Doesn't get much better than a Hermitian matrix. Only everything for Hermitian. Okay? So, that, by the way, that specialization of this matrix, of this theorem, when A is Hermitian, is known as the spectral decomposition theorem. And for a Hermitian matrix, the Schur decomposition is also called the spectral decomposition. And if you think about it, there's a very close relation between the spectral decomposition of a Hermitian matrix, of a Hermitian matrix, yes? And the singular value decomposition of a Hermitian. For those of you who are going to be in machine learning and things like that, there's a method known as the principal component analysis. In principal component analysis, people tend to compute the spectral decomposition, the single value decomposition of a matrix. But what you're actually computing is the singular value decomposition, because that matrix is invariably Hermitian. It's invariably symmetric. Okay, so everybody thinks that they're doing a eigenvalue decomposition when they're doing the principal component analysis, when what you're actually doing is a singular value decomposition. And it actually would be much better if you thought about it as a singular value decomposition rather than a spectral decomposition. Because it's actually the correct way. I'll have some exercises that actually, well, I know I have some exercises that tie all these things together.